check the audio?
Check the audio. Okay.
And then checking again.
Yep, there we go. They should combine this class with 430.
With data structures?
Yeah, make it a 740 because 310 plus 430 is is 740.
Hey, Professor. I don't know, because data structures, like, that was kind of time heavy. Like, how would you squeeze that and assembly into?
By programming smarter.
Well, we just need to come to class twice as often.
Either that or
4 days a week.
Alrighty. So, I'm not sure where the rest of the class is because, the homework assignment is due already. So I'm not really sure why people are still working somewhere else in the lab or something.
We thought you were going to extend that.
Or maybe their brain is so fried from the homework assignments, like, they cannot even get up to come to the class. But I'm going to get started anyway. Unlike the other homework assignments, what I will do today is to go through at least one or two of the subroutines that were in your homework assignment that's due today. So I'm not going to wait until the lab time to do it. But we will talk about the practice exam as well, the practice final exam, which is the main purpose of today's lecture. I put two more tar.gc files here. So in addition to cohort.tar.gc, I'm also including list and also bst. List is linked list, okay, and bst is binary search tree. So those things are kind of related to what you did for this homework assignment. So if you want to get some more exposure to those concepts, I think these are done already. Let me just kind of double check that. Let's see. Okay. So let me double check and see if these are already done. And I believe that is the case, but I can be wrong. So we'll double check on that one. EST. Nope, that's not the one. Might have saved it here. Oh, list. Okay, so these ones have not been done in assembly yet. Okay. This is not a new homework assignment, so don't worry about it. No, it is. No, this one is done. So when you look at node, where's the .c version? I think it's in main. Okay, so when you look into main.c, you have, we have make node, which is written in C. The make node.uppercase S is the assembly version of this. So you can use it as a reference, like, okay, how do we do something? In case you want to get some more exposure, this is one way to do it. I can even do it this way so that you can see it side by side. So we can do a -o main.c make node uppercase S. So when you look at these two, the subroutine make node, which is from here to here, is the same program in assembly from line 7 on this side, from line 7 down to this part here. So that's one thing you can do if you want to get some more exposure of how to do this kind of programming in assembly, which is going to be the focus of the final exam. So the final exam is going to be mostly focusing on pointers, structures, that sort of thing. Your homework assignment is actually studying. Okay, doing your homework assignment, was actually studying for this topic. So are there any questions about this type of thing? Make node is actually pretty easy. Print list is, let me see. What about print list? Do you think you can do it? If your final exam question is, okay, I give you print list, and you have to implement it in assembly, do you think you can answer that question?
No.
Well, the answer would be no at the beginning of the semester. By now, I think you should be able to do it. Okay, So what I'll do is I'm going to give you, we'll work on this one. This is kind of like, the final exam question practice, because, it's going to be something like this, okay? It is closely related to something like this. So what we'll do is we'll go ahead and implement that one. So we'll go ahead and edit print list dot uppercase s, okay? All right. So when you implement a subroutine in assembly, the way I do it, okay, it may not be the way that you do it, but the way I do it is to, generate all the offsets. Now the offsets to, individual members of the node is already done. In other words, if you look at the first program, it already has node.inc, okay? This part is done already. So when I work on the other program, I can just say pound include node.inc, which is the include file for assembly language. And then the next thing I usually do is to generate the offset to the various parts on the stack. Okay, node.inc includes offsets to individual members of a structure. These things are individual items on the stack in the call frame. Okay, so there is a major difference between these particular labels compared to what is defined in node.inc. Yep.
You can make these labels before you put dot text.
Before you do.
Dot
Yeah,
text.
you can do it anywhere you want. Label definitions, can be anywhere, unless it depends on the dot, which is where I am in that particular section. +4, and then we only have one parameter in this case, which is a plist, and that is return address +4. Okay, and now we are ready to specify the subroutine. Okay. So the way I write my programs is kind of not linear, because I would do something like this: move LESP to EBP, and then move LEBP to ESP. I do it this way because I write the matching instructions, so I would not miss the matching instruction for a particular construct. Yep.
Your dot global.
Dot global. Huh? Missing the dot global is going to be caught by the linker. The linker will catch that one, but it doesn't hurt to remember to do it here. All right. I do not have any local variables here, so that's okay. So what I'll do today is to illustrate a few common problems that people encounter, especially when they deal with recursive subroutines. Okay, because this one is recursive. Because when you look at print list, it is calling itself. Okay. All right. So let's go ahead and start with this one. So the first thing I need to do is to implement the conditional statement, and the condition is, well, it's kind of awkward. It depends on how you want to do this. With this one, you can invert the logic and just say, okay, if plist is pointing to something that is not null, then go ahead and do the printf and whatnot. Okay, so you don't have to do it exactly in the same structure as in this code. Okay, but regardless, we have to perform some kind of comparison based on what plist is pointing to. So that means the first mistake that some people make is to do a compare long $0 with plist EBP. That would not be correct, because now I'm comparing 0 to the parameter itself. But that's not what the C code is specifying. The C code is specifying compare 0 to what plist is pointing to. That asterisk, which is dereferencing, clearly indicates that I'm not comparing to the parameter itself, I'm comparing to what the parameter points to. So that means in assembly code, I cannot do it in one single line. There's no way to do this in one single instruction. I have to separate it into two instructions now. So the first one, and this is another common mistake. So I'm going to illustrate all the common mistakes, so that you can watch out for these things in the final exam as well. Okay. So the other one is, okay, we'll go ahead and use a temp register to do this. Okay, so I'm going to move plist EBP into EBX. Okay, that is a problem already. Okay, because if you read the documentation, especially the one that links to the Wikipedia page, it says EAX, ECX, and EDX are caller saved. All other registers are callee saved. What does that mean? What do you think EAX, ECX, and EDX mean when the Wikipedia page said it is caller saved?
They don't have the caller's value.
It means if the caller needs to retain that value, the caller is responsible to push and pop it. Okay? Now EBX is not one of those caller saved registers. It is one of the callee saved registers. What does that mean?
Any call function is responsible for
to save and restore, just like EBP. In other words, from the caller's perspective, EBX should remain unchanged. So the moment I do something like this, by trashing EBX, I can lead to a lot of problems, not in this subroutine, but in the caller of this subroutine. That's one problem that people encounter, and it will be difficult to explain because because especially when you write a subroutine that is called from C, because then you have no idea what the C code is actually, what it is using EBX for, and as a result, the corruption of EBX can lead to all sorts of problems when you get back to the C code.
I had this problem on my assignment.
With the one that's turned in today?
The complex one.
With the complex one?
Yeah.
Okay. So EBX, if you want to use EBX, you have to save and restore, which means at some point, before you change it, you have to push it on the stack first, and after you make use of it, after it is no longer useful, you have to do a pop EBX. So when you look at all the code between line 14 and line 17, which is not there yet, okay? But when you look at all of that code, you can do whatever you want with EBX because the line on line 13 is going to save it on the stack, and then line 18 will restore it. So as far as the caller is concerned, this particular subroutine is not changing it, even though we did make use of it. Yep.
13 is supposed to say ABX.
Say again?
Line 13 is.
Oh yeah, EBX. I'm sorry, I wrote EBP.
I did that so many times.
There you go. Thank you. All right. So are there any questions about about EBX? Who is responsible to save and restore it? Okay. Any questions? Okay. All right. So if EBX is going to cause so much problem, I'm not going to use it. I will use EAX instead. Okay. So that's okay, because you as a callee can change EAX, ECX, and EDX all you want. Okay. Because the caller does not make any assumption. Those three registers are retained by calling the subroutine. So the subroutine can use those three registers for whatever purpose. It doesn't really matter to the caller. Okay? But as we will see later on, we have another issue of using EAX, in this case. All right. So now that we have put plist into EAX, the comparison, which is this part in C code. Okay, this part in the C code, we can now do a compare long 0 with EAX in parentheses, because we are not comparing 0 to EAX, which is really just the parameter itself. I'm comparing 0 to what the parameter plist is wanting to, and the indirect operand is the dereference. Okay, are there any questions about this part? Okay, I hate to mention this. No food in the classroom, please. Okay. All right. So now that we have done the comparison, I have two ways to do this. The more straightforward way of doing it is to skip around the entire conditional statement when I don't have anything to do. So in this case, I really don't have anything to do when it does equal to 0. So I can say JZ to the end of the conditional statement. So and if you go here, and this part, what is remaining, is basically saying, okay, if plist is not pointing to no, this is what we need to do. Is that okay so far? Okay. So the first thing we need to do is to do the printf, which is this part here. When you do a printf, I have illustrated how to do this already. You can just basically say format string. Okay, you can use whatever label you want. .ASCIIs. Okay, now this time it is important to use .ASCIIs, or you have to ensure that there is a null terminator at the end. Okay, if you use .ASCII with II at the end instead of IZ at the end, then you can still specify a byte at the end that is a null byte. Okay, that's one way to do it, but this way is just more convenient. So I'm going to do it the clumsy way, which will still work. So in this case, we have %u \n and a double quote here. Okay, that part still works. Now you have the option. You have a few options now. You can basically go here and say .byte 0. Because everything is contiguous in memory, so that means this .byte 0, which is this one byte that is reserved and initialized to 0, is right after the line P character, which serves the same purpose as a null terminator in .ask keys, using that particular directive. Are there any questions about how I specify the format string? Okay, no questions about that. There's another way to do this too. It is a little bit more tricky, but it can be done that way, is to actually define the format string in the code itself. Okay, it's not really recommended, so I'm not going to do it here. All right, so now we have to push the last parameter needs to be pushed first. The last parameter is this thing here. So you look at this thing and go like, holy smokes, what is it doing? Well, let's go ahead and draw a picture, okay? Because a picture is always going to be useful. In this case, when you look at the type of the parameter plist, you can see 2 asterisks, which means it is a pointer to a structure. So when you draw a picture, it means in the plist, the parameter itself, which is using up 4 bytes on the stack, is a pointer, which means it is 4 bytes, it is an address of something. Fine, it is an address of something, but that something is a pointer to a structure, which means this something also has 4 bytes. Now where this thing is, we have no idea. It can be in the heap, it can be in the global variable area, it can be on the stack. But I don't really care where it is. I just need to know that these are 4 bytes, and these 4 bytes is the address of something else. These 4 bytes will be the address of a structure. So that makes plist a pointer to a structure. Is that okay? So once you have this picture and you look at the code here, we want to access value. Do we want the value of value as a member, or do we want to use the address of value in this case? Which one am I after? Am I after the address of the member, or am I after the actual value of the member? The value of the member, not the address of the member. Okay. So how do I get there? Well, there are 2 ways to do it. If you know the address of something, you can always get to the content, right? But if I don't want to use extra instructions, well, I can use the base addressing mode to get to this one really easily, because where is EAX pointing to? If I say this is EAX, okay, where does it point to? Does it point to this one, or this one? Well, okay, EAX is currently the same thing as a plist, so it still points here. Okay. So do I need to do something else to get it to this part here?
Well, +7 or plus whatever.
Now, because I only need the value, I can combine the dereference and the added offset, right? So now what I can do is I can say push L. This can be done with one single instruction because we have a cisp architecture. If you have a RISC architecture, you can usually not be able to do it in one step, then you have to do it in several steps. So in the final exam, sometimes I will give you a sequence of instructions, and you have to reverse it and say, okay, what does that actually mean in C? In other words, we'll be doing the reverse of what we're doing here. I will show you the assembly code, and you have to reverse it back to the C code. You will be taking on, sorry?
So that makes me feel a lot more comfortable.
That's hard to say. That is really subjective, so I cannot answer that question. So what I'm really doing is training you as a hacker, because this is what hackers need to do. They look at the assembly code. Assembly code you can get to write pretty easily. Okay, you can run any program in the debugger, and you can disassemble the program. Now, when you disassemble the program, it doesn't give you meaningful labels like else, and if, while begin, while end, or anything like that. It would just use generic label names like L0, L1, L2, and so on. But after a while, you will start to recognize those labels and go like, oh, I can see that these are related. It is forming a loop here. It is forming a conditional statement here, and so on. But these things, is another type of disassembling, because you're basically looking at the assembly code and then reversing it back to the C code. Why would anyone want to do something like that?
Because all programs
Because
are
we
in
want to
assembly.
pass this class, right? Yeah. Okay, besides that,
Because all programs are in assembly language, where you want to copy.
because that is the one thing they cannot protect, okay? Software developers cannot protect the software once it is released in executable, which is executable is basically in binary code, okay, in opcode, but you can easily reverse from opcode back to opcode, which is mnemonics, but from there to get back into high-level code is a little bit more difficult. It's a little bit more tricky. But why would anyone want to do that?
To get a source
Reverse
code of
engineer
any
something so
software.
you can sell it.
Well, that's one thing, and that's why reverse engineering something is actually illegal in the United States.
You just ask why.
Yeah,
Ask if it was legal.
that's one reason. But what about the other reasons? Yep.
Well, never mind.
To prevent reverse engineering.
To prevent.
So if you could do it and someone else can, so you can kind of like
Okay.
make it more difficult to.
Well, you can kind of look into the structure of code to see if any code is quote unquote borrowed from a certain source. Okay. So in the case of a class, you can use this kind of technique to find out whether there's any actual copying of code between the submissions. What about in terms of hacking? What about in terms of finding flaws in a program and that sort of thing? Exploits? Yeah. How do you, what about that? Can this kind of analysis help someone locate security holes of a particular program? And if so, how? If you can identify a loop, and you can definitely tell that in that loop we are incrementing pointers and we are overwriting stuff using that pointer, and the terminating condition is a simple compare byte to 0. If we do not see a null byte, don't stop copying, okay? Which is the typical way of doing string copy, okay? There you go, okay?
Information.
Yep. And it is also a security hole because it is opening up to Stack Overflow exploits. Now, Stack Overflow exploits do not work well anymore on many platforms because you can inhibit execution in data space. In other words, code that is pushed onto the stack space cannot execute. Okay, but you can still trash memory and actually do all kinds of other weird stuff that can still help reveal things in a particular program that should not be revealed. Okay, has anyone heard of the Heartbleed vulnerability that people discovered with SSL, the SSL engine, Open SSL engine? Okay, just so that you know why I want you guys to understand this kind of thing. I'm just going to go there for a very brief moment. So Heartbleed vulnerability. This was actually a pretty big thing. I like that icon. And the way this works is they keep probing. They use the quote unquote heartbeat ping. It's kind of like a ping to see if the other side is still alive, which should come back with a very simple reply. But because of the misuse of memory, it would come back and actually tell you something about the memory region. And depending on it's a probabilistic kind of thing what it actually comes back with, but there is a chance that it will come back with the actual private key of the key pair encryption. So once you get hold to the private key of SSL encryption, there's no point in SSL encryption anymore because once the private key is known to the outside world, then anyone can pretend to be that particular website. So. So you can read the rest, in Wikipedia. It actually has a pretty good detail of what the bug is. So let me see if I can find out the most important part of it. Okay, behavior. The affected versions of OpenSSL. Okay, Heartbleed is therefore exploited by sending a malformed heartbeat request with a small payload and a large enough length field to the vulnerable party in order to elicit the victim's response, permitting attackers to read up to 64 kilobytes of the victim's memory that was likely to have been used previously by OpenSSL. So it's basically the ability to probe the server and say, hey, give me 64 kilobytes of your RAM area. Now, those 64 kilobytes may map to something that is completely useless. But by repeatedly doing this, it might map to something that is actually useful. So that is the whole problem. But the problem of this has to do with failure to do proper bounds checking. Now, how can you tell from the assembly code whether some code is using proper bounds checking or not? You look at the condition of a loop. Okay, when do we get out of a loop? If it is only exiting the loop because it's looking for the terminating condition, which is usually the null terminator, it falls into this category. Okay. On the other hand, if you also use a counter to basically say, well, regardless of what you are giving me, I'm quitting after 256 bytes or a certain number, then it does not fall into this category. So by analyzing the analyzing the assembly code and being able to reverse it back to the high-level code can reveal problems like these. Okay. Are there any questions about this kind of thing? But why would you want to know something like that? Why would you want to be able to locate potential issues with a program by going through the assembly code, well, at least first by hand? Okay. But why is this useful? Thanks. We're talking about employment here, okay? Practical stuff, not your grade in this class. We're talking about employment, when you get a job, depending on what kind of a job you're getting, this can be extremely useful. Why is it useful? What is the fastest growing sector of computer science?
Security.
Computer security. Now, when we talk about security, there are different types of computer security. There's the security of how to flip a few switches in an operating system to make it quote-unquote secure, okay? There's that security, which is not unimportant, but there's also the security of being more preemptive, being more, how should I put it? Preventive and preemptive, okay? So preemptive is, to find out, problems with software that is used by other countries, other organizations, and be able to hack into those computers. Preventive means we are not going to release software or use software that can potentially have a problem. Is that okay? So once you know how to locate failure to do proper bound checking by analyzing the assembly code, then you will think, okay, but how do we do this to all these programs and operating systems that have megabytes, if not hundreds of megabytes of code? How do you do it? You cannot hire enough programmers in the United States to do that manually.
Write a program to skim it.
Exactly, because once you know how you do it, then you can start to write the software to do this type of analysis. You're looking for a certain pattern of a program. You're looking for a control structure that fits into a certain template, and say, if something falls into this template, it might be a problem. Okay? So now you're not actually doing it by hand. You're actually writing a program to analyze a particular executable and see if there are problems within the executable. And do you think a skill like that can be useful, is marketable, when you're looking for jobs? Just being able to talk about it in a job interview is going to be helpful already. Okay, so I'm hoping that some of you, maybe 10% of you, will kind of remember this part when you actually get a job interview.
Only 10%.
Nobody else.
I think most people would forget, because after the final exam, most people would just, nuke the hard drive and say I'm gonna empty out all this space, so we have more space for next semester. Reformat, exactly. Yeah.
Defrag.
Swipe, wipe it.
Yes,
Wipe it. Yep. Okay, so after we establish this context, why this is useful, so we now get back to this part here and continue on with this instruction. So what we are pushing here, there are several ways to express this. Okay, I'm going to use the first one, which is the easiest way to do it. So the easiest way to do it is to specify the offset to the member that we want, which is value, and then use EAX as our base register, because EAX is pointing to, let's see, that is not gonna work, is it? I need one more interaction first. So one more interaction means I'm going to copy whatever EAX points to into EAX. Because EAX at this point, before line 20, EAX is pointing to these 4 bytes, which is the address of somebody else. I'm not interested in these 4 bytes, by itself. So by going through line 20, I am now moving EAX not to point here, but now it's pointing to the very beginning of the structure that contains the member that I'm interested in. And as a result, on line 21, EAX pointing to the beginning or the base of the entire structure. If I just use the base addressing mode to add the offset, which is represented by the label node underscore value, I can now access these 4 bytes. So I'm pushing these 4 bytes on the stack, not the address of these 4 bytes on the stack, which is what printf needs. And then the next instruction is to push the string on the stack. That part is fairly easy because we already have format string declared earlier, which is on line 9. So we push that on the stack as well. We call printf. When printf comes back, we do the usual thing to clean up the stack. So we say add long $a to ESP to reclaim the 8 bytes used by the parameters. Now we are ready for line 25 of the C code, which is doing the other one. Okay, this one is interested only in the address of those particular bytes. So in this case, what are we going to do? Well, let's try the incorrect one first. Okay, node underscore p next EAX. What am I pushing on the stack?
The value of that.
I'm pushing the value of the member on the stack. What is the C code want? What does the C code want to do? Pushing the address. I'm passing the address of the member, as a parameter. Okay. So what you need to do in this case is to read the source code in the C code, carefully, and see how the parentheses are, nested. Okay. If you have any questions in class, okay, in the final exam about, the order of operation, you can always ask me to clarify. This is not a C programming class. I do assume that you have basic knowledge of C, but when it comes to the ordering of the operators, you can always ask me to specify additional pairs of parentheses to clearly indicate the order of operation. So in this case, you can see the ampersand applies to the entire thing. This parenthesis is closed all the way here. So I'm taking the address of whatever is specified between those 2 parentheses. What is inside? The inside is accessing a member of a structure that is pointed to by a pointer that is pointed to by the parameter. Okay? But we have most of that stuff figured out already. In fact, we have a pointer pointing to the base of the entire structure. So the only thing that is missing at this point is the address of that particular member. But line 29 does not get a trick done because line 29 is getting to the member and pushing the member itself on the stack, not the address of the member. So this is not going to work. What we do need to do is to specify the address. There are several ways to do it. You can always do a move L EAX to another register that is not supposed to be saved. I would use ECX or EDX. Okay, once again, if you use EBX, you have to remember to save and restore it. So that's why I try to avoid the use of EBX. Yep?
You call it printf, so this is your responsibility to make sure that's whatever in EAX you
That is exactly the problem of this code. Okay? So with this code, I'm assuming that EAX still has the value at this point, which is something I cannot count on, because remember what we said earlier in the class. EAX, ECX, and EDX are caller saved, not callee saved. I am the caller of printf, which means if I need EAX, if I need to retain the value in EAX, it is my responsibility to do something about it. I have to assume printf will trash EAX, ECX, and EDX. Those registers are free for the callee to trash. So that means this code may work, okay? If printf does not make use of EAX, I'm good. On the other hand, if it does, by the time I get to this code on line 29, EAX does not have the value that it used to have anymore, because it can be changed. How do we fix this problem? Well, we'll use EDX instead. Well, EDX falls into the same category. It's not going to work. So the way to fix this problem is to save EAX really early on. Okay. So what you need to do is to save it here before we push the parameters of the printf statement, and then you pop it here. Okay. Where you put the push EAX is also very important, because if you push it at the wrong place, it's not going to work. I'll give you an idea of the wrong place. That would be a wrong place. Because if you do it this way, then the value of EAX, which is the pointer to the beginning of the entire structure, just becomes the format string itself, and then the format string itself becomes the second parameter to printf. And so printf itself is going to do something that is really funky. It's going to print out wacky stuff on the screen, like this one. Okay. So that's why where you put the push L instruction to save the registered EAX is actually very important. Are there any questions about this program up to this point? Because I'm trying to step on every single landmine that is possible. That's the joy of assembly language programming. Yep. All right. So getting back to pushing the address of a member on the stack. So I can move EAX, make a copy of EAX to ECX after I pop it out from the stack, and then I can do the calculation by just adding the displacement of node underscore p next to ECX here, and then push that on the stack. Push L ECX. That would do the trick. Then we can call the subroutine, which is a print list, which is the subroutine that I'm defining right now. This is recursive. And after this is all done, we add L $4 to ESP to reclaim the space, and we're done. We are really done here. Getting to end of here is just the correct thing to do, and the entire subroutine is done. Any questions? Go ahead.
In this case, we didn't have to use ECX, right? Because we're not using EAX.
No, we do not have to use the ECX. But if you have any further code that makes use of the reference value of plist, you can keep using EAX throughout the program. But in this case, no, we do not have any further use of EAX. Yep.
In complex, instead of pushing EAX on the stack, I just did the values.
That's okay too. You can recalculate EAX. In other words, in this particular case, what you're saying is what we can do is not to bother with the push and the pop. So we can basically let go of this particular push and let go of this particular pop, and just move L plist EVP to EAX, move L indirect EAX back into EAX. So we can repeat those two instructions to get the correct value back into EAX first.
So which one would be more efficient, using two move L's or using push and pop?
In this particular case, it will be kind of even, because a push instruction is accesses memory, because you're pushing something onto the stack, and the stack is in memory. When you pop, it is another memory access. So you have one memory write operation and one memory read operation. using the push and pop approach. Using this approach, you have also two memory operands, right? Because the instruction on line 29 is one memory read operation, and then the next instruction is another memory read operation. So the only real trade-off is, you know, a write and a read, as opposed to two read operations. Assuming things are going to be cached, it's not going to be making that much of a difference. Yep.
To push the address, can we just push EX and then
Do the calculations on the stack?
calculations
Yes,
on
you
the
can do
stack.
it that way as well. So you are referring to these three instructions, right? Alternative to those three? Yes. So you can, okay, let me keep these three here, and then we'll compare the two approaches. So we'll say if define, you know, approach 1, okay, else, else. Then we'll describe the other approach. Okay. So the other approach is to push L EAX, okay, and then we do the calculation on the stack. That will work as well. So now we can say add long $note underscore P next, but this time you are adding it to wherever the stack point is pointing to, because it's the very same item that you just pushed that needs to be added to. So that will work as well. In this case, there is a clear difference in terms of efficiency. The code from line 32 to line 34 really only has one memory access, because it's only the push instruction that's going to write to memory. The other two instructions, which is line 32 and line 33, they are either moving something from a register to another register, or moving immediate into a register. In both cases, it does not involve a memory operand. On the other hand, if you look at line 36 and line 37, even though we only have two instructions in that case, the first operation, which is a push operation, accesses memory. The second instruction also accesses memory because we have an indirect operand. So in this case, the second approach, even though in terms of number of instructions it is shorter, it would actually be more, in terms of execution time, that might take up more time because we're accessing memory twice instead of once. And memory access is the bottleneck in many, many cases. So in this case, I would say the first approach is the more efficient one. In this class, I don't really care that much about efficiency, so they would both work. Okay, if you give me either, code, it is considered correct. Are we okay with this code? Yep.
Wouldn't it be 3? 1 to push, 1 to read, and 1 to write?
That is correct. You are very okay. That's very good, because the second operand is both serving as a read register at the beginning of the instruction, and also serving as a write operand at the end of the instruction. So you're correct. The second approach actually has 3 accesses to memory instead of 2. Good job. Any other questions about this code? No questions? Well, let's see if it works, okay? Because we don't want to write anything that, and then just say, well, we just make the assumption that this is going to work. All right. So if this is all done, we're going to go back to the C code, and what we'll do is we'll keep the prototype, and then we'll comment out the C definition, like so. And as usual, we go to the makefile and change it, so that we have one more program written in assembly, which is print list.uppercase s. And we'll do a make. And it does work. Are there any questions about this program? Let me just kind of show you the main program here. This is the main program. So what the main program is really doing is it's saying, okay, as long as I'm reading an unsigned integer, I will keep creating nodes and add those to a linked list. And as soon as I read nothing, okay, if scanf returns a 0 or -1, it means it is not reading an unsigned integer or has encountered in a file. In either case, I'm not getting what I want, and I will exit the loop. When I exit the loop, I will call print list, which is just going to print all the numbers already saved in the linked list. So this one is actually a much simplified version of what your homework assignment, because you cannot have a list inside a list in this case. It's just one level of a list. Right. Are there any questions about all of these topics that we have gone over? Go ahead.
Were you still going to do a version of one of the subroutines we had in homework?
Yes, we have plenty of time to do that.
Like node-append?
Hmm?
Like node-append or don't
Node append. Okay, so do you guys want to vote on which subroutine to go first? We have one vote for node append.
Sounds good.
Is that good? Okay. All right. So let's do that. So we'll go back to the homework assignment. What is the most challenging part of this homework assignment? Ooh, we should do this. We should do Dijkstra's algorithm in assembly. No, not really. Not really. That would be hard to do because. All right, so we'll start with the tar file. We'll do usually the same thing that we do. Let's give it in the 10 folder. All right, so we want to look at a node.c, and you guys want to do a node append, which is from line 18, which is here, all the way to line 30. That would be the subroutine that I want to implement in assembly. So let's do a node.c on one side, and we'll do a node append.uppercase s on the other side. So this way we do the usual thing, look at the C code on one side, look at the assembly code on the other side. You can see that there's really not a whole lot of variation I can do anymore. Even though this program does something that is quote unquote different from the code that we just saw earlier, but when you look at the parameters, like the one on line 22, it's the same thing, right? It has the same kind of structure to it. So it's going to use the same kind of approach. The trickier one is actually the other one, the one that has an indirect call. That one is quote unquote a little bit more tricky. But since I gave you the code to actually do the indirect call, it just kind of took the fun out of it. It's like watching a movie and I give you the ending already. That character is going to survive, but that one's going to be dead. You're like, no. I think that's why some people do not come to the lecture, because they can because they know that I'll give them little hints like that and spoil the whole thing, so they decide not to come to the lecture, so that when they watch the video, when I'm just about to give them the a tip of how to do something, they skip over that portion. They go like, I want to figure this out.
Yeah. Yeah.
Right? I mean, isn't that a good reason not to come to class?
Absolutely.
Yeah.
I thought you got this all.
Because I don't see anyone doing this during class when I go like, okay, let me give you a little snippet of code that might be helpful. All right, so we do a pound include, the usual thing. We pound include a node.inc, and then we do a dot global. The name of the subroutine is node append, and then we do the usual stuff. Old EBP equal to 0. Return address is old EBP plus 4, and then we have two parameters in this case. We have p me, pointer to me, is return address plus 4, and then we have new node, which is p me plus 4. So you will also be able to, you might actually see questions where I make mistakes in a particular implementation. And one of the mistakes that I can make would be the wrong order of these label definitions. So they're not in the right order, okay? So they're not correctly calculated to be relative to each other. I'm just telling you, you guys can do this, if you want the real challenge in the final exam. But I'm just telling you, all of these things, can be potentially type of questions that you encounter in the final exam. This is actually better than any practice exam questions that I can go through because it's going to be the same thing. Now, this is something that you have already worked on. Even if you cannot quite finish it, or you can finish it, but well, I just kind of did it by chance. Okay, it's useful because now that you have thought about it, just me giving you the actual solution can help you actually understand the concept. Well, what did I just do wrong?
You mixed up numbers.
I reversed the direction, right? It is completely opposite, okay? It's not easy to spot, okay? It's not easy to spot because they're still opposites to each other, okay? If I have, like move EBP to EBP, that's pretty clear, okay? But this one is not really as clear. So these are things that you have to watch out for because I can give you programs that are incorrect in these ways. This is another thing that can go wrong with a subroutine, which I actually accidentally demonstrated, I think on the first day that we talked about subroutines, right? What would be the behavior of something like this? It depends on what is the subroutine after node append, right? In the link order, okay? Depends on what is really after that, because it will be equivalent to calling node append and the next subroutine in sequence. Now, if the parameters so happen to work out also, then it's even more problematic because it's not going to crash. It will just do something that is weird, okay? So little things like these you have to watch out for. You might even come up with a list of things to watch out for, okay? Things that can go wrong, things that you need to kind of examine and make sure.
Are we going to correct the program you're writing here?
Sorry?
Are you going to correct the assembly program?
Yep, I will tell you that there's something wrong with this code. This is the C code, this is my the flawed implementation, and then you are responsible to fix it and not rewrite the entire code. Because some people say, it's easier just for me to rewrite the entire thing. No, I don't want you to rewrite the entire thing. I want you to pinpoint where the problems are.
So if we rewrite it correct way, it also works, is that right? If we rewrite the whole program to a new way, it's also right?
You have to identify what is wrong with it, step 1. Step 2, you have to fix it. Replace the wrong code with the correct code. So if you rewrite the entire subroutine, I would just count it as not getting the job accomplished because the job is not to rewrite it, the job is to find out what is wrong with it. All right, so now that we are in the subroutine, there are no local variables, so we are kind of easy that way. It has kind of the same structure as the other one, except this one does not say equal to 0 or not equal to 0 because it is implied. So in this case, we are going to do something like this. We're going to say, let's put the parameter into a register because we're going to use this register over and over again. So we'll put it into EAX. And then what we'll do is in this case, we can just, let's see. Since we're going to use it again and again, we might as well just put it do one more indirection. So EAX is actually the pointer to a structure now. It is not a pointer to a pointer anymore. Now it might be helpful to remember that. Okay, so it might be helpful to remember EAX is not PME. It is actually the dereference version of PME. Okay, when I write assembly code, I tend to also use commenting to remind myself what is in the register at this point, because it's not easy to keep track of all of these things while you also have the structure of the conditional statement and whatnot to deal with. Compare long a 0 to register EAX. I do not need an indirect at this point because I just did it before. J and Z, JZ, if it is 0, we go to the else case and we just put an else here. Since this particular conditional statement has the else branch, it also means that at the end of the then branch, I have to go all the way to the end of that whole thing. Okay. So let me just scroll so that you can see the entire structure. So missing the unconditional branch instruction on line 21 would be a fairly common mistake as well. Using J and Z instead of JZ is a common mistake. all of these little things you have to kind of watch out for because these are all very common mistakes to make. Okay, so now that I have the structure of the code done right, then we can specify the then code here, the code to execute for the then branch. We push new node on the stack, so we can just use that one, new node EBP, because we are just pushing the parameter itself on the stack. And then the next thing we need to do is to push the address of a particular member on the stack. So this is the part where you have to kind of reuse the same code that we talked about earlier. So we can say push L EAX, and then add L dollar node underscore. I think in this program I use uppercase N for the name of the node. P next sibling, and add that to whatever I just pushed on the stack. So now we have both parameters specified on the stack. We call the subroutine node append. When we come back, we need to add 8 to the stack pointer to reclaim those 8 bytes. Now, if you do not have if you don't have the instruction on line 24, the program is not going to crash. Okay, you just end up wasting 8 bytes on the stack. The program is not going to crash, but as far as the final exam is concerned, this is something that you have to be able to spot. Is okay, we are not reclaiming the space that is no longer needed. Okay. Yep.
You would have a problem if you're trying to use indirect ESP because you'll be accessing the part that you don't want.
Say again?
If you added, let's say you had a local variable.
Oh, but yeah, but none of the code that I have written so far relies on the absolute distance from the stack pointer to something else. Yep.
So even if like in your code you acknowledge that there's 8 more bytes on the stack, it's still wrong. Like later on you account for the 8 bytes on the stack. Instead of adding it now and then, let's say you just, if you're returning, let's say a structure, and instead of adding 8 now, you account for it later, and you still get to the right return address.
I think the bottom line is your subroutine going to use up more bytes than it needs to on a per frame basis. Now in this case, it's not going to use up any more bytes because that's the only subroutine call for the recursive subroutine call. So these 8 bytes, whether I reclaim it here or later on, it doesn't really matter because I'm not. There are no other subroutine calls up at this point. So not reclaiming these 8 bytes for parameters is not going to use up any actual 8 bytes on the stack. But the general principle is, when you are done with the subroutine, you should clean it up. Yep.
I think your label for your structure member or whatever in your thing is just node PMS.
Oh, okay. Well, I'll let the assembler complain about it, and then we'll fix it that way. Okay. Yep, I think that's the then branch, and then for the else branch, we have to do the 2 statements. PME is easy; it's already in EAX. That's the easy part. So now we have to store into P next sibling. Okay. Well, let's see what we. But that's also pointed to by new node. So new node itself is pointed to a structure, and this time we are just looking for we're storing something into a member that is, and the structure is pointed to by new node. Okay. Okay. How do we do this? There's a whole variety of ways to do it. Yep. Go ahead.
Use ECX or EDX to store the pointer and then dereference it.
That's one way to do it. I'm going to do it in a interesting way, okay? Because I want to give you guys as much exposure to alternatives as possible, because that will give you, this is how I help you get ready for the test. Okay, is to give you as many alternatives as possible so you can see, oh, okay, this will get the same thing done, this will get the same thing done, and so on. My office is doing the same thing, the tube is going out. You can actually now replace these fluorescent tubes with LED quote-unquote tubes that plugs just right in, and they make use of the current that is usually used to heat up the filaments on both ends. So instead of heating up the filaments to make it easier for electrons to go across the entire tube, the electricity that is usually used for heating up the filament is actually powering up the LED. So you basically have an entire bank of LEDs to take the place of a fluorescent tube. Which is it's plug in. It's really just plug and play. You just take out this tube, plug in the LED version of a fluorescent tube, and it lights up the same way without all the flickers. I think the school should start to invest in LED technology. All right, getting to the else part here. I'll do it the fun way. I'm going to push EAX on the stack. Now, what is EAX at this point? The entire right-hand side, right? I have already dereferenced PME, okay? It is already in EAX because we did that before we evaluated the condition of the conditional statement. So by pushing EAX on the stack, I have just pushed the entire right-hand side of the assignment operation on the stack. So at this point, I can mess around with EAX. I don't need EAX anymore. So at this point, I can say, yep, go ahead.
So how about after calling a load append, we write the data in the EX?
But that's the other branch. I'm on an alternate branch right now. So I now move new node, EBP, because it is a parameter, into EAX. And then we need to store something into a member of a structure that EAX points to. Because EAX in this particular case is not a pointer to a pointer, it is just a pointer to a structure. So that makes EAX itself also a pointer to a structure. It is pointing to the base of the entire structure. I can now use just the base addressing mode to get to the member that I need to overwrite. Yep?
If we use ECX, is that, don't use EAX, is that same thing?
Could you repeat that question?
I mean, if we use ECX instead of EAX, is that same?
Yeah, because they are for calling.
Are you asking why
Here,
can we still use?
else, I mean, else we push the EAX again, we go back to use the EAX. If I don't use EAX, I use the ECX another instead.
Her question is, she said we use a ECX instead of EAX, but our EAX holding a address of a PME at that time, so we need that.
There's no need of the old value of EAX at this point because I just push it on the stack.
So we have whatever there already in the EAX.
Right now, you mean after line 28?
Yeah, after 27.
After line 27, not E.
What's
Okay,
already
at the
EAX?
end of, okay, after you do the push L EAX, EAX is still the dereferenced version of PME.
Yeah.
But after line 28, EAX is new node, the parameter.
Her question is, can we use a ECX on the line 28 instead of pushing EAX?
Yes, you can. But what I'm going to do next is going to illustrate why I want to do it this way. I can now do a pop to node underscore P next. Okay, P and S. Okay, well, we'll see which one I actually use in the include file. X. Okay. Now, not counting the fact that I might not have been using or might be using the abbreviated version of next sibling, this is going to work because I'm using what I'm popping whatever I just push on the stack to the destination operand on line 29. But on line 29, what I'm popping into is not the register. I'm popping it directly into the member P next sibling of the structure that is pointed to by EX. So this is one way to do it. Is it the most efficient way? Probably not, but it is one way to do it. Okay? So I just want to make sure that you guys understand there are many, many ways to get the same thing done. All right. Any other questions? No other questions? Okay, the next line, which is line 27, seems to need EAX back to PME or the dereferenced version of PME. I I cannot do that. I cannot reuse EAX at this point because I have the value of the dereferenced version already, which is not suitable for the left-hand side. So in this case, I really kind of have to go do all the calculations again. So I would do kind of the same trick as the other one, but this time I'm pushing the parameter new node on the stack because that's my right-hand side. And then on the left-hand side, I first move PME EBP into EAX, and then I pop L indirect into indirect EAX. So that would do the same thing, okay? Because I have the entire right-hand side pushed on the stack, and then I move the parameter PE into EAX, but I don't want to store to the parameter itself. I want to store it to where the parameter points to. So that's why when I pop it to implement the left-hand side of the assignment operation, I'm popping it into where EAX points to, which is also where PME points to. So I'm basically using the stack to kind of help me out. Instead of using additional registers, I'm just using the stack to put something there and then I'll use it later on. All right, so getting back to the end if, this is another thing that can go wrong with a subroutine, forgetting to implement the return statement. Now, forgetting to specify the return statement is really bad because the caller will use whatever is in EAX as the return value. Now, in this case, the EAX actually has a dereference PB in it, so it is a pointer. It's just not the pointer that the caller is expecting, which is bad because if EAX has 0 in it or some value that cannot be used as a pointer, that's actually good news because the program will crash soon, which is good. This is bad because it does have a pointer. It points to some valid space. It's just not where it is supposed to point to. So if the caller makes use of the return value the way it is implemented right now, it's not going to crash right away. It will crash later on because I am storing something at the wrong place in memory. So really bad problems, okay? Not specifying the return statement. So be sure that we check, if the C code has a return statement, the assembly code needs something corresponding to it. So we need to move new node EBP into EAX because we use EAX to return the value of a subroutine, and I think that should do it. Okay. Let's go ahead and change the code here, and we'll see if it works. So pound if 0, and if, and then we change the makefile to, oh, and we have a whole bunch of stuff that is not done yet. Oh my goodness, we have to do all that stuff. This is node. Jan.c. Oh, that's just Jan. That one is Jan.c. And we look at the clean target and see if it's correctly cleaning up. Yep, looks like it is cleaning up. Alright, so now we look at Jan.c. That's not going to be very helpful. So I don't have it specified yet. That's okay. We'll just pound include node.h, and then we'll specify all that stuff here. Struct and f what is the other one? First child. I don't think I need first child just yet because the subroutine that we have done so far does not depend on it. And then we need to specify the label itself, node underscore p next sibling, which means I have to change this one here these things don't worry too much. Anything that the assembler can catch, I'm not too concerned. It's the kind of stuff that does something wrong at runtime that I worry more about. Equal to. Then we have
Just do P next sibling to save time for now. They should just do
yeah, that's all we need. Okay, that's fine. That is so typical of me. You know, as I said, this does not worry me much. If the compiler can find it, I'm not too concerned. Alrighty, so the moment of truth. Okay, one node is fine because it is not a list. Okay, so we'll run it again with as a list, and ABC is a. There are 4 nodes because the list itself is taking up 1 node, and then each one of ABC is taking up 1 node as well. So the program does work. Okay, are there any questions about node append? Questions? What is the biggest challenge of this homework assignment? Typing it. Okay, well, it's not really that long. I mean, compared to many other homework assignments, in terms of line numbers, number of lines, this is not too bad. What is the biggest challenge? What if the program crashes? Debugger, right? GDB is your best friend. Okay. How did you guys write these subroutines? Did you try to write multiple subroutines and try to debug all of them at the same time, or one at a time? One at a time, starting with the simpler ones, right? The simplest ones, first, because that gives you some confidence, and also it gives you the idea of, okay, the simple stuff I can do. Then you move on to the more difficult ones. Okay. Any other comments about the main challenges of this homework assignment? No questions? Right. Well, I kind of find it surprising because I think the majority of this class did not turn in something. So I'm expecting there are more feedback like, okay, I think it's difficult because da 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 da. How many people ran into like segmentation faults? That should be everybody.
Yeah.
I mean, everybody who tried will probably run into segmentation faults. Okay, I will run into segmentation faults if I would write a program like this. I mean, you guys saved me a few times. It's like, Jack, I think you needed to do this or do that. Okay, so the question is not whether you get a segmentation fault. You will. The question is, what if you get into what happens when you get into a segmentation fault?
Right. And dbx/.
You do it in GDB. And then you use the same test case. Okay, you use whatever test case you used when it crashed, and then you do it in GDB. When the program crashes in GDB, it will tell you at least something. If the instruction pointer, if EIP is something like 0, 1, 8, or something along that line, or it looks like ASCII code, it means your return address. You're using the wrong part of the stack as a return address. Okay. And what can be a potential reason of using the wrong part of the stack as a return address? What is the most likely cause of returning using the wrong part of the stack?
My home Linux get crashed several times. Words, they are look like different. If I press A, it show a totally different.
Okay. Okay, but go ahead.
Gave me problems the source of allocating memory incorrectly, so assigning things the wrong values, or not breaking up into symbols. You know what I'm saying. So at the beginning, when you create all your labels, not doing that correctly, and then you assume that you've done your labels correctly, so you use them.
Right.
And then that gets you into trouble.
Right. Or not having, missing the move EBP to ESP, that will make you use the wrong part of the stack to return as well. Because the whole idea of move ESP to ESP is to restore the stack pointer to a place where you say, oh, okay, I know exactly where where I am on the stack. That's it's pointing to OEBP, and 4 bytes above that would be the return address. But if you forget to do that, then you'll be using the wrong part of the stack as a return address, and the program will just go to some la-la land, but this time it will trash EIP, which is the instruction pointer. Okay. When you crash, if the EIP is not a problem, and it is one of the instructions like an indirect EAX that is causing the crash, then you have to track back, how you initialize EAX. And then at that time, you have to remember, if you call a subroutine right before you make use of EAX, you have to remember EAX is a caller saved register. That is one of the issues. What else? What other kinds of problems did you guys run into? Yep.
I had like infinite loops into
Okay.
it just kept printing stuff over and over.
Oh, right. And what was the reason for that?
I ran out of time to figure it out.
No. You keep asking about that one. I distinctly remember that particular problem.
No, that wasn't.
That wasn't you?
No.
Okay, then
That's
somebody
not-
else had the same problem. It keeps printing A, even though there's only one element A. Okay, so let's think about this, okay? Okay. So that one is for all. For all children do. Okay. So if the problem of this code or the translated version of this code is it does not move on to the next child, what can be the potential issues? This is the C code. The C code is correct, okay, but the assembly code somehow does not do the same thing. Okay.
Your condition of assembly isn't the same as what's there.
Okay, but what is the most likely issue? It is printing A correctly, so that means the indirect call is done correctly. Yep, go ahead.
PC was never updated?
PC is never updated. That is the main cause, okay? Because if PC is updated incorrectly, it will either give you gibberish or it will just crash, okay? But the fact that it keeps printing A all the time means the PC itself is not updated. So there's no storing back to PC, which is a local variable here. Okay, so that would be the first thing I check, is to see, okay, is PC a local variable getting updated? Because even if it's updated incorrectly, it will give you some symptom other than printing the same node over and over again. Any other questions? Yep.
Can you put comments in a makefile?
You can. Anything after a pound sign is comment. So that's a pretty universal way to comment stuff in Linux, Unix type of code. You do the same with Perl, Bash scripts, Makefile, our assembly code, and so on. So the pound sign is actually pretty much universally used for commenting.
Yeah. I just got tired, whenever I was on my last functions, if there was a mistake and I wanted to comment all of the other ones and stuff, just to be sure it's in this
I see. Well, the other way to do this is to make a copy of Makefile and then just mess around with the clone. Yep. Any other issues? Yep.
I said, challenge for me is it's hard to understand what's the P child, what's the symbol. If we could use like employee ID, staff ID, LC ID, like more normal information we use every day, not very high kind of information, that would be more easy for us.
I don't know. Okay, can you refer to a particular line of code?
No, I mean, usually we use like P next assembly. I was thinking about who is the assembly.
She doesn't know what the variables really mean.
Yeah, and it means I was thinking about long time. What, where, what happened?
You don't really
there?
need to know what it means.
Exactly. Okay,
Yeah,
now
maybe we can use a more normal.
normalcy is relative.
I'm normal language, not China. I'm not China.
Yeah, normal is relative,
I
and
want to know this class will never have to use it.
I really don't see how it is abnormal. I guess it has to do with me doing this kind of thing for
Yeah.
the past 15 years or so. Yep.
I think the deal is like, well, at least for me, well, like pretty much not having a variable with a meaningful name that refers to something specific, because it's kind of hard to keep. Like you gotta kind of keep ahead on like exactly which address you're on as you're stepping through the program.
Okay. Let me address that question. Okay, if I am to ask you, if this is all I gave you, okay, I gave you the definition of the structure, I gave you the prototype of all the subroutines, and I vaguely describe what the subroutines are supposed to do, and you are the one who have to come up with a C code to do it. Yes, in that case, I would say, well, maybe those names can be refined a little bit, okay? But that's not what you do, right? Your job is to take the C code and then translate the C code into assembly code, which is basically doing what the compiler does, right? Would the compiler complain if I just use ASDF, which is the consecutive keys on the keyboard, as a variable name? If I use it consistently, the compiler says, fine, not a problem, right? So that is the kind of thing that, that's, and I think, where and what is actually, correct, because where is saying, okay, where's the information? Where's the integer? Where's the string? What is saying, okay, what kind of a node is this? Is this an integer node or is this a string node? So it is, correct, I think, it's normal for me.
I think what they might kind of be getting at, something that I had a problem with and that I'm still working on, is before you start writing any code, just having an understanding of what the program does.
Okay.
So if you sit down and play with the program a little bit and see what these variables represent, what happens to them
I see
through
what
the
you mean.
program. It can be named anything at that point, and as long
Correct.
as you remember it, you'll be okay with it. But
P next sibling is actually the correct name because it is pointing to the next node of the same level. P first child is actually correct as well because it is pointing to the item of a sublist, but it's pointing to the first item of the sublist. So, sorry?
Where is the data file?
Huh?
Where is the data file?
Where is the what?
Or is it
Data
a file?
Yeah. Normally when I think about like a child, which have to under some tree and under some different, so I have to go file where the parents file from or where the child from, like that way. So I think I really spend a lot of time what
Because it is coming from a tree, terminology. When you have a tree, you have a node. So, with a tree like this, okay, this is called a parent, and these two are child or children of this particular node. So instead of doing it this way, I have the parent pointing to the first child, and the first child points to all of the next sibling points to the next one, and so on.
So if we just input A, B, C, D, E, nothing there, who is the parent, who is the child?
Okay, if you just input A, B, C, D, E,
Yeah.
A, B, C, D, E, without parentheses, then it is just going to take the A, make a note out of it, and then print it out.
Yeah.
It will ignore B, C, D, E.
Yeah. That's.
If you use parentheses, then it will start to understand, hey, this is a list. So what it will do is it will have a list as the parent node, and then the first child is the A, points to the B, points to the C, points to the D, points to the E, and the last one points to a null to indicate this is the end.
Yeah, I'm worried about it. It's like the final, we don't have computer, we can debug it, try to find out what's happening there. So we don't know what.
I can give you code that makes absolutely no sense. I only care about can you translate that into assembly. That really is the bottom line. I can give you code that makes absolutely no sense whatsoever. Okay, but syntactically it is correct. Okay, and in terms of type checking, it all works out. And I just want you to write the assembly code to implement it. Whatever the C code is, implement the same logic. But this class is about assembly language programming based on C, and that's what you will be tested on.
I mean, our case maybe can go more like everyday life case, not so the case we never use with
I use lists all day long. I mean, this is normal for me. These are data structure stuff that you in cisp310. This is the kind of thing that you guys have to implement too. I mean, this is. Okay, the prerequisite of this class is cisp 360. So, is any of this code using any feature other than C or C++? I don't even touch on C++, right? There's no C++ feature here. So that's what it is. I mean, you have to look at the C code, understand the C code, and be able to translate that into assembly code. Yep.
Curious, how are doubles and floats returned from functions? Are they returned through a return value pointer as well?
Say again?
When you're returning a double or a float from a function, do you do it through a return value pointer?
That is a good question. Okay, how do we find out when you have a double and you're returning it, how it is returned? Okay, so I know we are running out of time, but since there's really nothing to do during the lab time, I can extend the lecture time to 10 o'clock. No, we don't want that, right? Okay. Yeah. So I am going to illustrate how to do it, okay? Because this is useful because it not only illustrates so many of the concepts that we have talked about in this class, it also illustrates the process of how to figure out something, okay? Something that I do not know yet, okay? So what we'll do is we'll write a subroutine to do that. So what we'll do is we'll write a subroutine in C. Okay, so we'll say double.c, and we'll do it in C first. So we'll just go ahead and say double, and this is subroutine F, and all it does is to return 0.0. Okay, how is 0 represented as a double precision floating point number? All zeros, right? 64 bits of zeros.
No, isn't it offsets?
Nope. No, 0 is a special case. When you look at the double precision floating point format, if you just strictly use the rules of, okay, this is the sign bit, these are the exponents, and this is the fraction of the mantissa, there is no way to represent 0. So 0 is a special case. When all the bits are 0, it means the actual value of 0, and you do not break it down in terms of those parts to interpret it. Okay, so that's why I use 0 here, because we know what it looks like. Okay, all right, and we have the usual subroutine main, and return 0 here. And what we'll do is we'll call a function g, and function g is going to be written in assembly. Okay, so we'll just say void g, because it's going to be written in assembly, but we still need to specify the prototype in C just so that the C compiler is okay with it. Okay, so now we write g.s dot global underscore g. We don't really need this stuff at this point, but we'll go ahead and specify that. We don't have any parameters, so we have g here. Push L EVP, move ESP to EVP, call, what's the other one? F, and do a move L, EVP, ESP, pop L, EVP, and return. Okay, that's all I'm going to do. So what I'll do is I'm going to put a breakpoint on line 6, on line 8. Now I can cheat and actually trace into function f in assembly to figure out, how it is implemented. But that would kind of take the, that's not the point. The point is I cannot trace into it, and I want to use the side effect to figure out what is going on. Okay, so let's go ahead and do this. I'm suspecting it is going to be stored in EAX and EDX, EAX being the least significant 32 bits and EDX being the most significant 32 bit. But I can be wrong. This part I do not actually know. Okay, so I'm going to shortcut this whole thing and just use a GCC-G-O double.C and what's the other one? G.S. Okay, it all links. So go GDB double. Put a breakpoint in the code in assembly. Run the program. Now we are calling f. As I said, I'm not going to trace into the subroutine because I don't want to, cheat that way. So I'm going to say, what is in EAX? There are several ways to do it. I can print /x $EAX. It is a 1. Okay, that's good because if it is going through EAX, it should be changed to a 0. Okay, and we can now say what is in EDX because I'm suspecting EDX is also going to be used. And both of these are non-zeros. Okay, so if my suspicion is correct, after I do the call, both of these registers should be zeros. Okay, so we'll test it. Do a next, so we are not actually tracing through into the subroutine. Print EAX. It is still a 1, and EDX still has this, so it's not going through that register. So at this point, it is helpful to look at this one here. It's using some of the other registers. Could be ESI, EDI. EIP is the instruction pointer. Oh, you know what? There are floating point registers too. So it is going through one of the floating point registers, which is not displayed in this particular part. Yeah, so it's not quote unquote visible to us. That one I kind of know because when I glance through the notes, the C decal, C calling standard, how registers are used in the previous, in this one here, C calling convention. We just need to look for double. Okay. Okay, they're called. So there's a separate stack for floating point values. So I'm suspecting it's also using a different register to return the value. It's one of the floating point registers. So that's why we cannot see it with one of the registers that we are used to.
How do you access the floating point registers?
That is a good question. All registers. Right? Info, all registers. And so when you look at all the registers, this is not it. This is not, we're not done yet. So we have all of these other ones too. All right. So of all of these ones, I think it's one of the ST registers. So what we need to do now is to specify a different value, something other than a 1. So, if you can remember from your homework assignments, it's one of those other things, other ones that we talked about. Let's see. We can figure this out. Okay, so let's go ahead and return a 3.0, okay? Because that should be easy to spot as well. How do we represent 3 as a floating point number? We have forgotten everything about floating point numbers already.
3 is a floating point?
We're gonna take like the next 5 minutes. More than 5 minutes.
Okay, it is 1, 1, right? In binary. But if I normalize it, it becomes 1.1 times 2 to the power of -1. Yep, I think it's right. Times 2 to the power of 1. Because I shifted this way, so I have to use the power to compensate for it. Okay? So this is going to be the fraction. This is the exponent. But the exponent is offset by 1023, which means we're going to store 1024 as the actual exponent. The sign is a 0. The exponent is 1024 in 11 bits, which is easy because 1024 is exactly 1 followed by a whole bunch of zeros. Okay? And then we have this one here, which is a bit 51, okay? And then a whole bunch of zeros after that. So when you look at the grouping of these things, we have, this is a 4, and then we have 11 bits, so we have 0, 0, that accounts for the sign bit and the exponent, and then we get to the fraction here. That would make it 8, and then followed by a whole bunch of zeros. So this would be the representation of 3 as a double precision floating point number. So we'll be looking for this particular pattern in those registers when we change this instruction to return 3.0. Okay. By the way, this is also reverse engineering. These are basically techniques to find out how something works. Put a breakpoint into the subroutine G, run the program, call F, info all registers. Oh, that doesn't work. And there we go. ST0 has it. There's a C instead of an 8. A C is 2 bonds.
4, 8, 12. So down to the 4, 8, 12.
Okay, the 4, 0, 0, 0. Okay, so we have 0 as a sign bit, and then we have the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is the exponent, right? So we have 4, 0, 0. And then after that should be the exponent. So that should be a 1 here, which is an 8. Why is there another 1? Because this is 3, and this one is not represented. Maybe that's not actually in double precision floating point representation, but something that's close. It is. This is bugging me. Okay, let's count the number of hexadecimal digits here. The value is okay, we got it, okay? It's just that the representation does not match what I'm expecting. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, oops, I miscounted. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 bytes in it, not 8. So that's not the usual double precision floating point format. This register is a floating point number register, but it's not using the 64-bit double precision floating point number. It's using, what I'm suspecting is it is not normal, is not keeping track of only just a fraction, it's actually keeping track of this one as well. So it's some sort of internal representation so that it's easier to do calculations, actual calculations. So let's find out whether that is the case or not. Okay, Intel register ST0. Okay, so we have ST0 here, but it doesn't break it. Okay. It's an 80-bit, okay, that accounts for the 10 bytes. And it stores numbers in the IEEE floating point standard double extended precision format. So it's not the double precision format, it is the extended version of it.
So 128?
Hmm?
It's a 128?
No, it's 80-bit. Right here it says it's 80-bit long. So now we look at this number here, we look at this name.
I think it's a 128-bit.
So this is how I spend my time, when I do, fun stuff, is open up new tabs and new tabs and new tabs. Okay, extended precision refers to floating point number format that provides greater precision and more exponent range, and that accounts for the extra 0, right? Because we should only be seeing 400, but we're seeing 4000, so that gives it 8 more bits for the exponent. So it can specify a larger range of values. And it does not keep track of just the fraction, because if you look at the, I'm looking for a summary of the actual format. Okay, so right here, this is a 1 is always there. So it says, basically right there, it says that 1 is always there. And that accounts for the C, because instead of having just a 1 here, we have 1, 1. 1100 is C in hexadecimal. So now I feel a lot more comfortable now that I can actually explain. Even though it's not in the scope of this class, I don't like it when I cannot, understand why is this like this, and I'm expecting something else. So there you go. Yep.
Is the one that makes it more precise, or because it seems like it's an extra bit that can be used to store that in?
That is correct. It's already longer, so the fraction part is 63 bits instead of 52. So that means it is already having higher precision than what we can really store as a 64-bit double precision format number. So for internal calculations, it is more precise already than what we can store, which is fine, right? But what is happening here is with this extra 1 here, it makes calculation easier because you don't have to say, oh, there's assumed to be a 1 there, and then whenever you do the calculation, you have to artificially put that 1 back in order to do addition, multiplication, and stuff like that. It is already there. So it saves time and also silicon, inside the processor, so it doesn't have to deal with that special case that like, oh wait, there's always an implied 1 point here. It is actually explicitly represented in this case. So that's why the internal representation is using 80 bits, so it doesn't need to compact and squeeze all the bits. And it's already more precise than what it can store, which is the bottom line. Is we cannot store these 80 bits into a 64-bit number. So, are there any questions? I don't know about you guys, but I actually I found it kind of fun to figure out how a double precision floating point number is returned.
Is that one of those registers? Is that one of those registers you talked about?
It's ST0, which is a floating point number register, which normally in the good old days of the 386 processor, it does not belong to the processor itself. It belongs to the floating point unit, FPU, which is a separate chip that you can install in the process in a motherboard. Starting with the 486 processor, they start to put the floating point unit and the rest of the processor onto the same die, and that's when it becomes standardized and say, oh, we can assume those registers to be there, because you cannot do that with a regular 386 processor.
Do they change the size? So on a 32-bit, those STOs are 32 bits.
I think those have always been 80 bits long, 80 bit wide.
80 bits.
Yep. ST0 is 80 bit wide. Yep.
I noticed somewhere that it said that the floating point registers are used as a stack. They're organized as a stack or something.
There's a separate stack for the floating point unit, and there's a separate set of instruction to deal with the floating point unit. And in this class, we only talk about the non-floating point unit instructions, but there's a separate instruction. There's a separate set of instructions only for the floating point unit, which is kind of messy in a way because it is extending the instruction set itself to. So the processor now basically is. In the good old days, when we still have like the 386 processor, the main processor, and the 387 co-processor, what happens is, certain type of instructions, the processor will basically say, I don't know how to do this. And it will just, send those instructions over to the 387 floating point unit to do the calculation. When that thing is done, it will come back and tell the processor, I'm done, and the results are here. But now, when we have the floating point unit and the main processor being on the same die, the mechanism is still the same. We're still going through the same mechanism, so the architecture is backward compatible, but they're actually on the same die now. All right, any other questions? That would make an interesting question for the final exam. One of the members of a one of the members of a structure is a double precision floating point number.
For next semester, not for us.
Alrighty. Any other questions? But the focus of the final exam is C to assembly language conversion. Okay, particularly with structures, pointers, and I didn't really quite go through arrays, so I'm gonna let that go and not really use arrays in the final exam. Yep.
So it's not going to be so much concerned with hardware or things that we did at the beginning of the semester, more just flattening the C code.
Yeah, we'll be mostly dealing with the flattening C code.
Will there be adder stuff and the logician that we did in the first half?
I don't know yet, but my inclination is not to, have those questions.
Sweet.
So I can focus on, this stuff. Yep. Interrupts. Interrupts is a concept. The only thing that I can test you on is how to write something and how to read something. So, setting up the registers to read, setting up the registers to write, I can still quiz you on those particular topics. Those are already, okay, well, I just put it here, so I cannot say it's already here. But remember last time we actually, tested that, so that's basically it. With writing, you set up register EAX to 4, you set up EBX to 1 for standard output, and then ECX is the pointer to where you're writing from in memory, and then register EDX is the number of bytes that you try to write to standard out. For reading, you specify a 3 in EAX, and the rest of the registers still do the same thing, except you're not writing from memory to a file, you're reading from file into memory. And that one, I just linked it in today, and it is here. It's in the reverse order, so interrupt and system services is actually should be the first one. Linux call table is the second one. And like that. I'm just clicking on the link, just so that you know where it is. So common surfaces, file output, and this is the code to do it. Okay, yep.
So you're going to cover these topics too? Are you going to cover these topics in the final?
Yes. Yep. I cannot give you a particular homework assignment just on this one because it's kind of easy. The only part that most people forget is EAX is the return value. So it tells you how many bytes was actually written or actually read when you get the callback. Any other questions? No other questions? So it will be kind of a variety of topics. As I said, some questions I will give you the C code. I'll give you the wrong implementation in assembly, and you have to pinpoint what the problems are and how to fix those problems. There will be another type of question where I give you the assembly code implemented correctly, and I would even try to use labels that make sense, like while begin and stuff like that, or not. But then you have to reverse it back to the actual C code. Okay. And the tricky parts of those things would be the pointers, members of a structure. Those are the tricky ones. Those are the ones you have to kind of draw a picture and keep track of the registers. There'll be So that's reverse compiling, and that's the usual compiling, which is I give you the C code and you give me the assembly code. So those three are definitely going to be there. Okay, I'm just kind of going through my mind and trying to figure out what other type of questions I might be asking.
It's like other tests we can use those, right?
Yes, it is open book, open notes, no electronics other than a scientific calculator if you want to, and I'll bring my bag of easy, simple calculators as well. I don't think it's going to be that important, but if you want to have a calculator, I'll bring my bag of calculators. It's open book, open notes, no electronics. I cannot think of anything else. I mean, you really need to be. What you need to do is to make sure you understand all of the concepts that we talk about in the class, and bring the notes, just to help you in case you cannot remember some details.
We have example. Practice the example.
We just did it.
The one, so we are going to have this similar one, another type of, like for example, we're going to reverse from assembly back to the C code.
Yep. So, well, I'm pretty sure most of you cannot remember exactly what the code of these, the code that I have just written. So you look at the assembly code and then you say, okay, can I reverse it back into the C code?
So you want we read the assembly code and write the C code?
Say again?
You want us read the assembly and then write the C?
Yes. Okay.
Let's see Thursday. No, Tuesday.
So the way you do it is to look at the control structures. Okay, how do you spot control structure stuff? Okay, I'm just gonna labels, and there's one more type of thing that is clearly indicative of a control structure, or it's a part of a control structure. Jumps, unconditional branches, and conditional branches. How do you identify a loop?
Relationship with labels and jumps.
Okay, so if you have a jump going back to an earlier point, that is almost definitely going to be a loop. Okay. Now, what about a while loop versus a do while loop? How do we differentiate those two?
If there's a condition that's required to get into the loop, then it's not a do.
Okay, if you see an unconditional branch back to the beginning, that's almost going to be a while loop, because a while loop has an unconditional branch to go back to the earlier part. A do while loop, on the other hand, has a conditional branch back to the earlier point, because you are using a decision to say that after the body of the loop, then you make the decision and say, should I go back should I go back to that label? So it's going to be a conditional branch going back to the earlier point. Okay. So those things will clearly indicate that we are dealing with a control structure. Okay. How do we know that we are dealing with pointers and stuff like that? What is a clear indication that we are dealing with a pointer or the dereferencing of a pointer?
The direct addressing mode or?
Indirect addressing mode or the base addressing mode, those are indicative of using a pointer or using dereferencing. Okay. So there are all of these things that you can clearly you can actually just kind of go, okay, these things belong in a certain at a certain place. How do you know that we are dealing with a function call?
Just call.
Well, but sometimes I cannot have the call instruction, right? Okay, so keep that in mind.
Those subroutine
parameters.
A label.
Yeah. Also the ones we always do. The move along ESP,
All the
EVPs.
setup.
Right. Well, that's setting up the call frame, right? That's for setting up the call frame. But within the call frame, you have to use something in parentheses EVP, so that would refer to a parameter or a local variable. Yep.
So how are we gonna know that it's simple integer or it's a pointer?
That's a good question. Okay, so the question is, how do we know whether we are using a register as a integer or whether we are using it as a pointer? If you see the referencing, it is a pointer. If you do not see the referencing, then it can be either one. Okay. How do you differentiate between a unsigned integer as opposed to a signed integer? What are the only clues you can use in order to say, okay, I know this parameter is signed or I know this parameter is unsigned?
Conditional.
Yep, the only time you can tell is when you have conditional branches, okay? And only when you are only with the ordering type of conditional branches. If you're only checking for equality or not, there is no way to tell the actual difference. If you're adding and subtracting, there's no way to tell those two types apart. But when you have greater than, less than, that sort of thing, then you can tell. Because JG, JNG, JL, JNL, they all belong to one side, and then JA, JB, JNA, JNB, they belong to the other side. Okay. Any other questions? I mean, you're basically exercising all of the things that we have learned so far, and you're basically looking at the assembly code and say, okay, do I understand the behavior of this assembly code? What type of C code will match that type of assembly code? That is basically what you need to do. Okay. Any other questions?
How many pages do we have?
I do not know yet.
So what's the hour, 2 hours?
You have 2 hours. You have 2 hours in the final exam. It goes from 8 to 10 o'clock.
So when is the final?
Next Tuesday.
It's in the syllabus.
Yes, sir.
Good try.
Like,
Well, I still have office hours every single day. So if you need to talk to me, come to my office hours. Tomorrow is the last day of instruction, so my office hour is still from 8 to 9 o'clock. Most of the days of the final week, I still have office hours at the same time, 8 to 9 a.m., except for the one day that I have an exam during that time, then I move the office hour to after the exam.
is that like 5 in the afternoon, some actual real hours, 5 in the office, 5?
Before class, no office hours?
I mean, afternoon time.
The final exam starts at 8 o'clock. So I'm not going to be, I might be in my office at about 7 o'clock on that day, but if you need to talk to me, you have to send me an email to make sure that I will be there. Yep.
Is there a practice final exam?
Well, we just kind of went through all the concepts, but if you want to know the actual kind of question that I might be asking.
Actual questions or kind of?
These are actual questions from previous semesters. So this is one from 2013 spring, so 2 years ago. So when you open up this one, let's see. Okay, I'm gonna do it this way. Save from as temp. Okay. So just unzip that folder, or then it's a zip file. 2013 is a zip file. We go to okay, there we go. So we have the 6 questions, and in this particular year there were exactly 6 questions, and each question is really in the form of source code. So the question is in the comments of the source code itself. So I can give you a general idea. This is on Moodle already. Okay, so you can actually take a look at it. So in this case, I'm pretty sure it's the forward one, to compile the code. Yeah, I'm just trying to find the question. I think that's the solution already. Yeah, that is the solution. This is the question, how do we implement readnum? And the solution is in readnum.uppercase-s. So that's the answer. Okay. The next question. Now, given these solutions, you can actually do it in 2 ways. Okay. You can look at the assembly code and try to figure out the C code, or you can look at the C code and say, okay, what is going to be the assembly code corresponding to the C code? Because both are in the folder already. So you can actually work on it in either direction. You can practice it in either direction. Here is Q2. And in Q2, Okay, with this one, it is the implementation again of the subroutine F, and the actual implementation is in F.S. So once again, the assembly code and the C code are both available. So if you wanted to see if you can reverse it, you can test whether you can reverse it. If you want to test whether you can go in the forward direction, you can do that as well. Q3.
It's all going to be on paper, right?
This is all going to be on paper. Yep. Which makes it very fun for me to grade. Yep.
Wait, don't you have less time to grade it during the spring? Don't you have less time to grade it during the spring?
Not really. I think I have to turn in all the grades before the end of May.
Okay.
Yep. So that's not really a whole lot of time. Yep.
On the homework of the no delete, you have a counter specified as a signed 32-bit integer, but returning a unsigned 32-bit integer.
Correct.
Is there a particular reason for that?
No. No particular reason for that. So in this one, we have multi-item.s, which is that's the okay. This one I leave holes here so that you can fill in the blanks. Okay, to correspond to the actual code, which is in one of the .c files. So I'm going to guess it's main.c. Yep, there you go. So this one resembles, this is not resembles, but this is complex.
Oh.
Yep.
I don't think everyone in class caught it, but last lab you pointed out that to return a structure, you had to do that. You had to deallocate.
The callee is responsible to deallocate the last parameter, the first parameter, I should say. Yep.
Yeah, first parameter.
Yep. Which is this one does not have that either. Let's see. Question number 4. So this one has this one subroutine to be implemented in assembly, and the actual implementation is init inc.s. So these all have solutions in it already, but you can use it in either direction. Question 5. This one has the string end compare. Okay, I give you the C code. You have to implement in assembly code. And then the last one is big structure. So we have main.c. This is the subroutine that you have to implement in assembly, but this one has arrays, so we're not going to do arrays in this class because we haven't really spent much time on it.
Is there a huge difference between arrays and structures like return?
Well, it is big. There's a big difference because with arrays, how you specify the element is by indexing.
Oh, yeah.
And then with structures, it's just the name of the member that you want to access. So with arrays, the big thing about an array is the way you specify which element you want to access within the array is based on the expression inside the square brackets, which can change at runtime. With structures, you cannot change which member you want to access. It is always going to be a particular member. So that means the way we use arrays is different from the way we use structures. They serve different purposes. Okay, so that's one, and I think there's another one too. 2013 spring final exam solution. So this is the actual, okay, great. These are the actual questions. So the following code is written in C. This is an attempt to implement in assembly. So the crossed out parts are the wrong parts, or the parts that are corrected. So this is kind of the nature. I give you the wrong code, you have to fix it. So this is missing in the original code. The pound sign, the dollar sign. The offset of the set stack is wrong. I have to fix it from 4 to 8. Yep.
So is there any without corrections? So is there any questionnaire without
I don't think
corrections?
so. I don't have a version of
it
that.
already has corrections. So
Yeah, I don't think I have one that does not have the correction. Yeah, there's another practice one here, so we can take a look at this one. It's a tar.gz file. Okay, so this one has the instruction is actually a part of the comment. So the instruction is write a subroutine sum n in C using only structured code. This means statements like go to, break, continue are not allowed. Because I don't want you guys to use the flattened version of the C code. So you have to give me actual structured regular C code. So the code is already written in assembly, and you have to give me the actual C code. This is the assembly code, and you have to give me the C code. That's the first question. And then the second question is Q2.C, and the question is to implement this subroutine in assembly code. So that would be LSTRRM, okay, long string remove, and you have to do it in assembly. Is there anything here that we haven't seen before? It's all the same stuff over and over again, right? Okay, so this is question number 2, and here's question number 3. So question number 3 says the following implementation does not work, at least not for all cases. You have 2 tasks. The first one is to find out which cases it will fail. Find test cases that will make the program not work correctly. Note that some problems may not show up due to the addresses of string 1 and string 2, or the values of the extra bytes after the null terminator. So you actually have to kind of analytically find out what can go wrong with this code. For those problems, catch them and fix them, but there's no need to document the failing cases. The failing cases, string n has this value, string 2 has a certain value, the exit code is incorrect, it should be this, but the program would actually exit with a different value. So you have to tell me, how you can test the program so that it does not work correctly. The code is down here. Okay, this is the C code, and this is the assembly code. So you have to figure out why the assembly code is not working. Okay. That's question number 3, and let's see, question 4. That's it. So the practice test only had 3 questions, in that year. But that's kind of the general idea of what kind of question you can expect to have. Any other questions?
Can you go back to the 2013 exam where you crossed out the wrong assembly code?
I can do that. I can probably undo the crossing, but I'm not 100% sure that I would do the undoing part correctly.
So page code down a little bit.
Yeah.
So you crossed out the start as a function and wrote it after the format string.
Because originally it was here.
Yeah, so you can't have the format string inside the function.
You cannot, because if I had f:" here, when you call the subroutine, it will try to execute the bytes representing %x \n as if they are instructions, but they're not.
Yeah, okay.
So there's a chance that nothing is going to happen, but most of the time it will do something wrong.
Okay.
Yep.
Can you repeat that? Why it should not be there?
Because this is the entry point of the entire subroutine. And the bytes immediately at this label would be the ASCII code of %, the ASCII code of lowercase x, and the ASCII code of the line feed character. And then the program will try to execute those bytes as if they are actual instructions. And that's not going to work. In general, it does not work. Okay. And then the rest of the program, these are new. Okay. In other words, in the original code, these 2 lines were missing. Okay. And and the program just ended with a return. This part, was originally a 4, and it had to be corrected to an 8, and so on. That's the first question.
Is that the way we correct there?
Yeah.
So we just cross 4 and put an 8 there?
Yeah. Yeah, you just use a pencil or pen to do it. And then question number 2 is The following code is written in C. You may assume labels are properly defined for the structure. The assembly implementation is half-baked, which means it's not done yet. It is just sort of done. Fix any mistake you find and finish the code to push the second parameter of the scanf call. So that means when you see the red ones are erasing, and then the beige ones are additions. Question number 3, assume the following struct definition in C. Assume labels are properly defined. The following code is used to push a parameter on the stack and then call the subroutine F. Assume F does not return any value. How do you write this subroutine call in C? So I just want the call itself. So this is the actual call in assembly. I want you to do it in assembly. So the correct answer is write the prototype of the C function. This is the prototype. It is a double pointer, and the actual code of the call is this. Yep.
So how are you gonna figure out from assembly code it's like it is using a double pointer?
How can we know it's double? Or single?
You draw a picture.
From the assembly.
No, you draw a picture like this. Use the assembly code to help you draw a picture like this. Then you look at the picture and say, okay, if I have a picture like this, what do we use in C to represent that picture? Well, that's why C is the prerequisite of this class.
So this is for double pointer,
Pointer to pointer.
Yeah, if it's a not pointer to pointer, we don't have the middle one, is that right?
If you only have one pointer to a structure, then you don't have the intermediate one.
The middle one.
Okay. And up here.
What's that?
It's color coded. Okay, the whole thing is color coded. 1 is red, 2 is beige, and 3 is green.
Do we need to do that picture any test?
Hmm?
Do we need to draw that picture any test?
No, I'm explaining the answer. Using color coded pictures. Okay, so I think this one is self-explanatory.
Yes.
Sufficiently so. Okay, question number 4, assume the following definition in C, usual stuff, yada, yada, yada. But this one has to do with arrays. Don't worry about it. I'm not going to ask any array questions. Question number 5, the mul instruction only works for unsigned numbers, blah, 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 blah. There is a signed multiplication instruction. Assuming there is none, implement signed multiplication using instructions that we have discussed. Okay. In other words, this is the C code, okay, and this is the assembly code. In this particular case, you have to do it. You have to do both. You have to both do it in C and then do it in assembly. Because the assumption is you only have unsigned multiplication. So if you can only do unsigned multiplication, how do you use that to implement signed multiplication? Well, you take care of the sign first, make everything positive, do the multiplication, and then fix the sign after that. All right, so question number 6. Assume the following C struct. Someone wrote the following code in assembly language. Decompile this code into its C equivalents. Okay, well, it is color coded, which means red goes to red, green goes to green, beige goes to beige, blue goes to blue, gray goes to gray. So I'm not gonna show you the actual code because some of you actually might want to work on it. So I will let you guys print this out and work on it. All right. So I think this is actually a pretty good representation of what kind of question I can ask.
So,
yep.
Now everything is on Moodle?
This is all linked in Moodle right now. Yep.
So like you say, you can find answers.
It's right here. This is the link. That's actually the final exam used in 2013 spring. Any other questions? if you did your homework assignment, you should be okay with most of the questions. Yeah. Yep.
Do you have any recommended references for learning more about?
Not really. I mean, you know, the whole thing about assembly language programming is there are only so many instructions, okay, you know, that we have talked about in this class. So the only question is, how do we combine those instructions to do what needs to be done? And the idea is, you know, this is the C code, this is what we want to do, these are the instructions that we can actually use. So how do we use these instructions? Limited, you know, in each one, you know, how do we combine these instructions to accomplish what the C code is specifying? So understanding that C code is assumed, okay, and then, you know, the synthesis of the assembly code is the real challenge of this class. Is what I'm really assessing is, can you synthesize the assembly code or recognize the assembly code and say, oh, okay, this assembly code is that in actual C code. Okay. Any other questions? And you can bring these with you too. Okay, if you can bring the solution to all the past exams, you know, with you to the actual final exam if you think it's going to be useful. Which usually means, you know, I would try to make sure that it is not. Well, but there are only so many things I can do, right? There are only so many variations I can do, okay? Because I'm still limiting myself to C code and assembly code. I mean, I'm not going to get out of that, you know, boundary. So there are only really so many things I can do to change the type of questions and the structures and stuff like that.
Try your best.
Or as Anakin said to Obi-Wan Kenobi, you may try, right? All right, any other questions?
The final ones, if you can send us. Is there any question? Please send us.
Okay, if I find any, I'll go ahead and send you guys some.
Are you gonna curve the final?
It depends on whether there is a need to do it.
But if everyone's getting on the lower end.
What he said.
What I usually do is I look at some quote-unquote benchmark, you know, students who have been working hard in the class. I can see they're getting the material. But if many of those students, you know, are, you know, falling into a grade that I think they do not belong to, then I adjust the scale so that these students get to the right places. Okay. And then the rest of the class is just pulled along the same way. Okay. Yeah. But typically the way I adjust grades will not benefit people with a score of 0. It mostly will benefit students with a score of, you know, 60% or so. You know, they can potentially bump up to the next one. And you still have to remember the breakpoints of the grade, you know, yes, where the A, B, C, D, F are, you know, just so that you do not look at your percentage the same way as your other classes. Yeah. Then you know, I would freak out too. Yeah. Alrighty, well, I'm gonna stop the recorder and get everything uploaded. As I said, I will still have office hours. If you guys need to ask any questions, do not hesitate to come to my office hours. And we still have lab time today. I don't know what you guys want to do, but I am going to the lab until, well, for about half an hour.
I'm going to eat something. I don't eat since this morning.